Hello and welcome. Today's topic is earthquakes. This is keeping in line with our surface of the earth and the plate tectonics. Some general terminology: the focus is where the earthquake originates. It's where the plates are actually touching and the stress builds up. When the stress overcomes the lock that they have, the plates suddenly move and waves radiate from the focus. Now, being we're surface creatures, we're more interested in the epicenter, which is directly above the focus. Earthquakes occur because the movement of plates cause stress to build up, and that stress is suddenly released. Waves radiate outward from this point of stress. So they occur at fractures or faults. The stresses build up over years and then they're suddenly released. The energy propagates in all directions. I did mention waves. Waves is one way energy travels. P waves are compressional waves. S waves modulate perpendicular in an up and down, and then surface waves travel on the surface. Seismographs can read all three waves. Generally, the surface waves dissipate quickly, and the body waves travel through the earth and can be detected far away. A seismograph is the instrument used to detect earthquake waves. P waves travel faster than S waves, so the P waves are the first to reach a earthquake station. The further the time is between the P and S wave, the farther the earthquake is away. You can use that time lag, or difference between the P and S wave, to determine the distance to the earthquake's epicenter. So you need to find the arrival of both, determine the difference, and then using a graph, you can find the distance to the epicenter. In this class, we will be using two types of graphs. So here is an example of how we do it. You can see our seismograph stations and the distance. Just by looking at this, you can see station C would be the closest because it has the less time lag, and station A would be the furthest because it has the greatest time lag. So station A was data taken from San Francisco. You get the arrival times and then the time difference. In this case, the time difference is 4:10. Denver, Colorado was station B. Again, you need 3 stations to determine the epicenter. We'll see that soon. There are your arrival times, and the time difference is 3:20. Our last was in Montana. It has the shortest arrival time. The time difference is only 2 minutes. So you chart the data on the data table. Now you have the time lags. Now there's 2 different graphs. This one's a little more complicated, but you can get the most information. So using the difference between S and P, you cannot use the time on the y-axis. You have to use the gap between them, and you can see step 1, make a little piece of paper, and then you measure the difference between the 2 lines, and then you can use that to find the epicenter distance. In this case, it is 2.8 times 10 to the third, or 2,800 kilometers. Like I said, this is a more versatile but more complex graph because it keeps the P and the S wave separate. You can find a lot of different information using this graph. So the epicenter distance in this case is 2,800 kilometers. The second graph that we use, and this is the one you'll use on your test, I have both in your reference tables because it boils the information down. You just take the time lag and it tells you the straight difference. You don't have separate S and P. This is a time lag graph. So using those graphs, this is the epicenter difference that we have. Now you use a compass in lab, or you can use a little sheet of paper or a string, but you measure each distance separately from the scale at the bottom of your map. Then you trace your circles around each seismic station. Where they meet, that's where the epicenter is. Notice in San Francisco, our distance was 2,800. So anywhere on that circle could have been the epicenter. Our distance varies from station to station. You need 3 to triangulate. And when you have 3, you can locate the epicenter. So a single seismogram just tells the distance, so you need 3 stations to triangulate your epicenter. Now, the different types of faults that we look at, a normal fault is a dip slip. I remember dip means changing in the vertical direction. So a normal fault is a dip slip. So notice this is from expansion, so they're moving apart. A reverse fault is also a dip slip, but one is being pushed up over the other. And then a very acute reverse, a thrust fault. The last type of fault is a strike slip. It does not change in the vertical direction, just the horizontal. A left lateral means the plates are moving left. The plate you're facing is moving left. A right lateral, the plate you're facing is moving right. So you have dip slips, normal and reverse, and strike slip, transform. Earthquake intensity measures the damage done by an earthquake. We use the Mercalli scale, and there it is listed. Most of you are probably familiar with the Richter scale. Now, the Richter scale, we use a seismograph and a chart to figure it out. This is the chart. You draw a point at the epicenter distance. You measure the amplitude of your seismograph. Then you connect those dots, and where it crosses on the magnitude, that is the Richter scale. Earthquakes are very destructive. It varies from earthquake to earthquake because of not just the intensity, but the substrate, the soil, whether it's solid or whether it's damp or moist, but buildings, fires, tsunamis under the water, and then landslides and other mass wasting events can occur. Even the time of day can make an earthquake more destructive. Rush hour traffic versus the middle of the night. So there's a lot of factors that go into the destruction caused by earthquakes. The most destructive earthquakes in history can kill up to 1 million people. If the substrate is loose earthquakes can be amplified. If it's solid, they can dissipate quicker. So again, what the wave's traveling through can determine the earthquake severity. And again, soil can liquefy if it's moist, and you can see here the soil liquefied, and apartment buildings actually toppled. Tsunamis occur mainly from underwater earthquakes or volcanoes. Other things can cause a tsunami as well. They're also called seismic sea waves. They are not tidal waves because tidal waves are tides. The one in Indonesia, one of the more famous ones, the Holiday earthquake, which occurred the day after Christmas in 2004 and claimed the lives of over 250,000 people. You can see it originated in the Java Trench, and then the wave propagates outwards. It hits Indonesia in a matter of seconds, but it takes hours to reach India. So depending on your location, you can easily avoid death by moving to higher ground. 26 nations comprise the tsunami warning system because tsunamis are most prevalent in the Pacific Ring, the Ring of Fire. So 26 nations rely on each other for tsunami detection. Now, it is impossible to predict when an earthquake occurs, but you can estimate the probability of earthquakes looking at the area and looking at the past earthquake occurrences.